In this video, we would like to talk about why the Lagrange multiplier method works for functions of two variables. So let's see. The statement says, assume f of x and y and g of x and y are differentiable. F has a local extrema on the constraint g of x and y equal to k at point A and B. Gradient of g of a and b is non-zero vector. It's not a zero vector. Then there exists a scalar lambda such that gradient of f of a and b equal to lambda gradient of g at a and b. So one thing that I want to mention is that whenever we are saying that the gradient is non-zero vector, and here also we're assuming lambda is not a zero value. This is so that the definition of two vectors being parallel would work also. Now, so the sketch of the proof goes like this. Here, what this means is that this is an objective function on this constraint, and then at point A and B, with which the local extrema exist, and it's on the constraint, we want to say that gradient of G and gradient of F, this statement means gradient of G and gradient of F are parallel. So the first thing is that here, G of X and Y equal to K means that I have a curve that is this constraint. Let's parameterize that curve. How do we parameterize it? By X of T and X equal to X of T and Y of T. And typically we show it as a pair and sometimes in this format. The next thing is that this curve, parameterized curve, at a point will spit out point A and B. At a t value, at some t value, it spits out A and B. Let's call that t equal to 0, such that X of t0 is going to be A, Y of t0 is going to be B. Therefore, R of t0 is going to be A and B. Now, if I take, now let's plug in this R of t inside of F, because every time we're finding an optimization on a constraint, it's really, we use a parameterization and we plug it in there. So let's say G of t is equal to F of X of t and Y of t. If I use the chain rule, basically a G prime of t is going to be equal to F sub X at X of t and Y of t times X prime at t plus F sub Y at X and Y times Y prime at t. Now, what is happening is that because this G, now that we made a composite function G of t, this G of t at a local extrema should be 0. So G prime at t0 has to be equal to 0. Now, write this out. I'm going to get F sub X of X of t0, Y of t0, X prime at t0 plus F sub Y at X of t0, Y t0 times, let's write it here, Y prime at t0. Here, let's rewrite it. I'm going to get rid of that part, right? 0 is equal to F sub X. This is going to be equal to A. That is going to be equal to B, X prime at t0 plus F sub Y at A and B. Again, same reasoning, t0. The next step is I'm rewriting this as the product of the gradient times something else. So 0 is equal to gradient of f at a and b, because these two make the gradient, dot x prime of t0 and y prime of t0. And then at this point, I'm basically saying, because this x prime, y prime, which is r prime at t0, is in the direction of the tangent line. Therefore, gradient of f at a and b is orthogonal to the constraint, to the curve of the constraint. Therefore, gradient of f at a and b should be is parallel to gradient of g at a and b. And then that's the final result, because that's how two vectors are parallel. One is a scalar multiple of the other.